All right, today we're going to do a little bit of a throwback. We're going back to limits. There's some limits that we have not dealt with yet, and let's go ahead and jump into that. Speaking of throwbacks, let me remind you of a little bit of something from pre-cal class. These limits at infinity that we're going to work with relate directly to horizontal asymptotes as studied in pre-calculus. For example, whether you remember or not, this is something you talked about. If you have an f of x that is equal to an x squared minus 1 over an x squared plus 1, and you were in pre-calculus class and you were being asked questions about horizontal asymptotes, the way that was explained, at least the way it's usually explained in the typical pre-cal book, is you're supposed to look at the degree of the numerator, and on top you have a second degree polynomial. On the bottom you have a second degree polynomial, and since the degree of the top is equal to the degree of the bottom, your horizontal asymptote would have been y equals 1, that 1 coming from the ratio of those two coefficients, 1 over 1, giving you this 1 right here. That is the way it is typically done in a pre-cal class. And you're not usually offered any explanation as to why that's the horizontal asymptote. If you were to look at the graph itself, it looks something like this. And if you sketch in a horizontal line hitting the y-axis at 1, you'll see, and my artwork is not the best because this should not be coming back down, it should be going up, staying up, because what you see is you move off indefinitely in the right-hand direction, meaning as you move towards infinity, and as you move off indefinitely in the left-hand direction, meaning move towards negative infinity, you find that that function will pull closer and closer to this horizontal line, the one running through the 1, and once it pulls in close to it, it will not pull away from it. It will literally get infinitesimally close to that line, y equals 1, as you move off in these two directions. In other words, what they are trying to say, what I'm trying to say, is that on this right-hand side, what we're seeing is that the limit of x squared minus 1 over x squared plus 1 as x approaches infinity is equal to 1. This horizontal asymptote discussion that you had in pre-calculus was really nothing but a limit in disguise. Over here, we see that the limit of x squared minus 1 over x squared plus 1 as x approaches negative infinity equals 1 as well. Again, all the time that you spent discussing horizontal asymptotes, you were really doing nothing but limits in disguise, sort of a watered down form of limit. In general terms, when we say that the limit of a function f of x as x approaches infinity is equal to L, what that is basically saying is that as the function travels off in this right-hand direction, there is a horizontal line that this function is traveling towards, that's being pulled into. And once it gets pulled in close, it will never leave. Same thing if we were to say limit of f of x as x approaches negative infinity is equal to L. We're saying about the same thing. We're saying that as the function moves off in the left-hand direction, it is being pulled closer and closer to that horizontal line. And once it gets pulled in so close, it will never pull away. It will get infinitesimally close. It'll go as close as you want, and again, never depart. So how are these limits found? Well, there's a small handful of, let's call them tricks or techniques that are used. And my intention with this section is simply to show as many examples as possible. I'm going to go through multiple examples just so you can see these techniques being put to use. They all relate, or most, if not all, relate back to one theorem in particular. If we have a R value that's greater than 0, then the limit as x approaches infinity of 1 over x to the r will be 0. All right? And on the same note, the limit as x approaches infinity on the negative end of this same 1 over x to the r will also equal 0. All right? That theorem is given so that we can just put it to use without proof. But I would like to at least convince people that it works. All right, so let's say I was going to take specifically the limit as x approaches infinity of 1 over x squared. I'm going to pick an r value of 2 just for the sake of the example. And maybe the calculator can convince us that the limit is what they claim that it is. So I'm going to hit my y equal 2, put in the 1 over x squared. And I'm going to do this through the use of a table. So we're heading towards infinity, so let's get started. At 1 over x squared is equal to 1. So again, this theorem's trying to claim that that's a 0, but we're not at 0 yet. When I put in a 2, I'm at a quarter. When I jump to a 10, I'm at a tenth. I'm sorry, 100th. When I jump to 100, when I jump to 1,000, when I jump to 10,000, as you can see with the scientific notation, the output is getting smaller and smaller and smaller. So what is happening in essence is I'm taking the 1 and I'm dividing it by a large number. Then I'm taking the 1 and dividing it by a larger number. Then I'm taking the 1 and dividing it by something that's even bigger. All right, let's stop and think about what's going to happen as this process continues. When you take 1 and divide it by increasingly large numbers, what's going to happen? Well, I'm already at the point where I have a decimal, 7 zeros, and then a 1. That's pretty close to 0. As a matter of fact, if you said, well, how close to 0 can you get? I can get as close to 0 as you want me to get if you just allow me to use whatever x value I choose. I can get as close to 0 as you want. And of course, it works the same way on the negative side. So you may ask, well, how does this help me with all these other limits? Well, again, there's a little bit of a trick to it. All right, so let's start. Let's say I had the limit as x approaches infinity of a 3x plus 5 over x minus 4. All right, I'm going to look for the highest power found anywhere in the fraction, and that's a first power in this case. I'm going to divide top and bottom by x. You'll get to the point where you just simply do this in your head, but for now, I'm writing it out. Whoops, there we go. So 3x plus 5 over x minus 4, dividing top and bottom by x. This is the limit as x approaches infinity. 3x over x is a 3. 5 over x is 5 over x. X over x is a 1. And there's a 4 over x. Now I use the theorem. Theorem says basically a constant over a power of x is a 0. Constant over power of x is a 0. 3 plus 0 is 3. 3 over 1 is 3. All right, so there's basically the first technique, the first trick in your little bag of tricks, and that is to divide everything by the highest power of x before you try to use the theorem. So if I had the limit as x approached infinity of a 2 minus 3x squared over 5x squared plus 4x I would divide the top and bottom by x squared. So you'd have a limit, as x approaches infinity, of a 2 over x squared minus just a plain 3, because the squared cancel out, and a 5, and a 4 over solitary x, because one of them canceled. All right, as the theorem says, as x approaches infinity, this one zeroes out, that one zeroes out, and all that's left is the negative 3/5. All right, so there's technique number 1 for you, dividing by the highest power of the variable. All right, well, let's try another one that follows those lines. Let's look at the limit. As u approaches infinity, just to show you that x is not the only variable in the world that can be used, a 4u to the 4th plus a 5 over a u squared minus 2 times a 2u squared minus 1. Now with this one, do I have to multiply out that denominator? Not really, all right? You could, I'm going to write down something that you could just do in your head. All right, the 4u to the 4th plus 5 is okay the way it is. But in the denominator, if you multiply that out, your very first term is going to be a 2u to the 4th. All the other terms are going to be of lower powers, so guess what? They don't matter. When I divide top and bottom by u to the 4th, all these other terms are going to turn into zeros. So I'm going to get a 4 on top, that term will zero out, and a 2 on the bottom, and 4 over 2 is 2. So it boils down to only the highest powers matter. That is all. All right, now, next problem type. Let's look at something a little bit different. I've got one here that says limit as x approaches infinity of an x plus 2 over the square root of 9x squared plus 1. And again, our technique has been, our little trick has been, divide by the highest power of x. And you may look at this and think, well, the highest power of x is going to be the second power. I have an x squared here. No, you really don't. You have the square root of x squared. And the square root of x squared is basically absolute value of x. So the actual power is just a first power. So I divide top and bottom by x. Kinda. I divide the top by x. I divide the bottom by the square root of x squared. And again, remember, that's the same thing as the absolute value of x. Well, on the top, it gives me a 1 plus a 2 over x. On the bottom, that gives me the square root of 9, because the x squared canceled the x squared, plus a 1 over x squared. And again, don't forget your limit notation, which I almost did. This turns into a 0, this turns into a 0, that's 1 over the square root of 9, which is a third, all right? So the ones with the square roots are pretty straightforward, as long as you remember that the square root of x squared is absolute value of x. Also remember, absolute value of x is an interesting definition. Absolute value of x is equal to x itself, or x's greater than or equal to 0. Also remember the absolute value of x is the opposite of x, or x's that are less than 0, meaning negative. So if I was to take a problem very similar to this one, if I was to take the limit as x approaches negative infinity, if I go in the negative direction with a problem just like this, square root of 9x to the 6th minus x over x cubed plus 1, all right? Again, remember, the highest power here is not x to the 6th. Highest power here is square root of x to the 6th, which is x to the 3rd. So on the bottom, I'll divide by x cubed. On the top, I divide by the square root of x to the 6th. All right, so I'm going to have the limit as x approaches negative infinity. Here's what happens on the bottom. X cubed divided by x cubed is a 1, plus 1 over x cubed goes here. All right, and the square, and what's going to happen on top is x to the 6th will cancel x to the 6th. X over x to the 6th is a 1 over x to the 5th. But what will happen is, since I'm heading towards negative infinity, since I am dealing with these negative x's, then I have divided by basically the absolute value of x here, which is the same as the opposite of, absolute value of x cubed, which is the opposite of x cubed. So basically, you have to introduce a negative sign in front to account for the fact that you divided by an absolute value on the negative side of the x-axis. So what will happen is that'll 0, square root of 9 is 3, and over a 1, and again, don't forget the negative sign. Okay, do not forget the negative sign. All right? So watch out for that negative sign. It trips a lot of people when they're doing those limits on the negative side of the x-axis. All right, so next, what should we do? Let's look at the limit as x approaches negative infinity of an x plus square root of x squared plus 2x. All right, so what's going to happen with this one? With your limits, there is a lot to be gained by understanding, by knowing what graphs of these particular functions look like. All right, for example, right here I have an x squared plus a 2x. X squared plus 2x is going to be a parabola. And as x approaches negative infinity, that means you're moving this direction along the parabola. So basically what's going to happen here is x squared plus 2x is going to head towards infinity, upwards, as x heads towards negative infinity. And then next function we have is a square root function. Well, square root function looks like this. And if you put an infinity inside of a square root function, that means you're heading along the graph in this direction. And it's going to head towards infinity. So in other words, what I have here, just sort of doing some real bare bones plugging and chugging, is this portion of the answers heading towards infinity. But over here, if you just plug in for x, you see that this portion of the answer is heading towards negative infinity. So I'm in a situation where I have a negative infinity plus a positive infinity. That's where I am. And I will give you one huge warning. You do not, at least not at this point, want to get into a position of doing arithmetic with infinity. There will be some that we do, and there'll be a bit that we never mess with, right? But if at this point in time, if you're looking at a negative infinity plus a positive infinity, or infinity divided by infinities, or infinities times infinities, you do not want to mess with that, right? A lot of people are going to think infinity plus negative infinity, they're going to cancel each other out, and you're going to get 0. And you do not want to think that way. Okay? That is a very, very deep hole that you're digging. You cannot do that. So what we're going to do is we're going to rewrite this thing. I'm going to make it look like a fraction. And I'm going to multiply top and bottom by the conjugate. Okay. All right, here we go. So now what happens? Okay, on top, first times first is x squared. And again, I'm foiling here if you hadn't noticed. First times first is x squared. Outer product is minus x square roots of x squared plus 2x. Inner product is plus x square roots of x squared plus 2x. Last times last will be a minus, and square root times square root will cancel. And on the bottom, I just have the x minus square root of x squared plus 2x. Okay? What happens is that cancels that. Agreed? Those cancel. Yes, they do. This is the limit. X approaches negative infinity. All right, here's what else is going to happen. The x squared minus the x squared will cancel. The negative sign will distribute. And we've got an x minus the square root of x squared plus 2x. All right. Now, I did all this mainly because the technique I showed you involved you dividing top and bottom by a specific power of x. Well, I didn't have a top and bottom. My fraction didn't have a top and bottom. So that's why I could use the conjugate to create a fraction and to get rid of some stuff that I didn't want. This plus thing up here was a negative infinity plus infinity scenario. I didn't want that. I didn't want that. So the highest power here is the first power. So I'm going to divide top by the first power. And here, I'm going to divide bottom by first power. All right. But look what happens. Look what happens. When I divide on top, negative 2x divided by x is just a negative 2. All right, so that cleans up a little bit. X divided by x is just a 1. All right. Here, when I divide, since I'm heading towards the negative side of the number line, all right, I'm heading towards the negative side here. The negative and the negative will make a plus. And I'm not just dividing by x, I'm actually dividing by the square root of x squared at the same time. This is going to become a 1 plus 2 over x. All right, again, when I multiplied here, I just multiplied as a, when I divided here, I just divided an x by an x. When I divide here, I divide by a square root of x squared, which pulls the negative sign out front that we discussed earlier. Now, what happens as x approaches negative infinity? Well, this zeroes out. On top, I've got a negative 2. On the bottom, I've got 1 plus the square root of 1, all right, which is a negative 2 over a 2, which is a negative 1, which is what that all ultimately comes out to equal. All right, again, mainly remembering that when I divided here, I was dividing just an x. When I divided there, I was dividing by the square root of x squared. And since I was heading to the negative side of the number line, that's why the minus turned to a plus. All right? And a constant over a power of x, that turns into a 0. And the new part of this, the new technique, the new trick, was the multiplication of the conjugate. When you see something plus or minus a root like this, it's quite common that a conjugate is going to get used. The trick that I showed you, we divide by high, or the highest power of x, is used in other situations. If I had the limit as x approached infinity of 1 minus e to the x over a 1 plus 2 e to the x, I'm not going to divide by the highest power of x. I'm going to divide by the biggest thing I can find, which is an e to the x. All right, so this is going to give me the limit as x approaches infinity of a 1 over e to the x minus a 1 and a 1 over e to the x plus 2, all right? And if you're familiar with the function e to the x, it's an exponential. It's the exponential. As x approaches infinity, e to the x goes to infinity. So once again, we're in a scenario here where we're taking a constant, dividing it by an ever, ever, ever rapidly increasing value. In other words, that zeroes out, so does that, and we'll get a negative 1/2 out of this. All right. Now, there are quite a few of these limits, though, that again can be done. You can do them the way the book does them, or you can use what you know about functions. For example, if I had the limit as x approaches negative infinity of x to the fourth plus x to the fifth, a lot of books would advocate that you say, well, this is the limit as x approaches negative infinity of, they would say, well, pull out an x to the fourth, and that leaves you 1 plus an x to the fifth. All right. And from there, since this is an even power, they're going to say that as x approaches negative infinity, all right, x to the fourth is going to approach an infinity times, and a 1 plus x to the fifth is going to approach a negative infinity, and a negative times a positive gives you a negative. That's what a lot of them are going to say. I would prefer to say, well, x to the fourth plus x to the fifth. Here's my preference. That is a fifth degree polynomial, and the coefficient, the leading coefficient, is a 1. 1 is your leading coefficient. Therefore, as you head in the negative direction, we already know the end behavior of a fifth degree polynomial with a positive leading coefficient. We know that as you head in the left-hand direction, that goes downward, right? So just from my knowledge of the graph, just from my knowledge of how polynomials work, I could have just gone ahead and said that's negative infinity. We already know what that function is going to do. We already know the end behavior of these polynomials, right? So a bit of a measure of common sense has to be used when working with these. But again, I do advocate staying away from infinity arithmetic, at least for the time being.